We will resume Lesson 11 with the pulley. Let's start this lesson with a video.
Good morning. Dear Tim and Moby, I need an example of a pulley. From Jimmy. Well, the pulley is what's called a simple machine. And simple machines like the lever, wheel and axle, inclined plane, and pulley are the most basic of tools. They each have one basic function. They're simple. When you want to open a window blind, you pull down on a cord. Your pull is called the effort force. The weight of the load exerts the resistance force. The blind has a wheel fixed to a support. This is our pulley. A rope runs over the wheel and attaches to the blind. The blind is the load that you want to move. Pulling down on the rope can lift the load as high as its support. Well, it wouldn't be as easy if you had to stand on the windowsill and lift that blind by yourself. You don't think so, huh? Try lifting that boulder over there. Pulleys work by changing the direction of the effort force and letting you use your body's weight to support that effort force. Single pulleys, including our makeshift pulley here, have a mechanical advantage of 1. For every meter Moby pulls the rope, the rock raises 1 meter. That means that the effort force and the resistance force are the same. Well, that's true. Some of the effort force is used to overcome friction. A single pulley doesn't increase your effort force, so if an object is heavier than you are, you won't be able to lift it. But if you have a double pulley system where one pulley is attached to a fixed support and the other is attached to the load, a person, or robot, can lift the load several times his or her weight. With one fixed and one movable wheel at work, the force raising the load doubles the effort force. The effort force needed is now 1/2 the resistance force. Moby now has to pull the rope 2 meters to get the weight to move 1 meter, but it's much easier to do because he spreads his effort out over those 2 meters of rope. The amount of work always remains the same. When you decrease your effort force, you have to exert that force over twice as much rope. With work, you always get what you pay for. Oh, that's not going to be good.
On the bottom of page 52, you will find the section to put your notes about the pulley. A pulley is a wheel and axle designed to lift objects. It has 3 parts: the rope, the load, and the effort. A rope or chain is placed over the wheel to make lifting objects easier. And the more pulleys used to lift something the easier it is to lift because the weight is spread out. You may pause the video, complete the notes, and then resume the video. We resume the video with talking about gears. A gear is a rotating wheel and axle that have teeth or cogs which mesh around another toothed part in order to transmit an applied force. This is on the top of page 53. Once you take your note down, we'll watch a video. So pause the video and finish your notes and then resume.
I'm in worse shape than I thought. Why, you little... Dear Tim and Moby, what are gears and what do they do? From Stan. A gear is a device that transfers motion from one part of a machine to another. Most gears are wheels or cylinders. These are sometimes called cogs. Just about every machine with moving parts, from clocks to cars to DVD players, uses gears. Gears usually have teeth on their edges that mesh together. When one of them turns, it forces the other gear to turn with it. Gears can also be connected by a chain, like on this bike. You often see little gears paired up with bigger gears. One reason to do that is to increase torque or turning power. Well, big gears turn with more power than small gears. The larger the radius, the more force a turning wheel has. Gears take advantage of that difference. Check out this electric car window. Like many machines, it's driven by a small motor, which doesn't use up a lot of electricity. These little guys spin really fast, but without much torque, definitely not enough force to move that heavy glass up and down. To increase the torque, you attach the motor to a gear train, a set of 2 or more gears. The gear connected directly to the motor will be small, and the next gear in the train will be bigger. In this gear train, the smaller gear has 12 teeth, and the bigger one has 36. That means the small gear has to turn 3 times to turn the big gear once. So we say that this train has a 1:3 gear ratio. Right, the big gear turns 1/3 as fast as the little one, but with a lot more torque. So you're trading in rotational speed for force. Gear trains set up this way create a mechanical advantage, magnifying the amount of force put into them. Think of it this way, you could stop a car window's motor with your fingers, but not the window itself. You can add more gears to the train to get higher and higher gear ratios and more output force. Oh yeah, gear ratios work the other way too, trading in force to gain speed. Like in an electric fan, you want as much rotational speed as possible. To do that, you set up a gear train with progressively smaller gears. On a bicycle, your legs are the motor. You use a big gear in front and a small gear in back to get more speed, and a small gear in front paired with a big gear in the back for more torque. Well, gears can do lots of other things too. When 2 gears are directly engaged, what do you notice about them? Right, they spin in opposite directions. Anytime the direction of a mechanical motion needs to be reversed, you can just add another gear to it. That's useful for any machine that has to be able to move in 2 directions, like cars or electric drills. And not all gears are round, by the way. These specially shaped bevel gears are used to change the axis of a machine's rotation. That's especially useful in cars, where you have to translate the motion from a shaft spinning down the middle to the wheels. And this worm gear rotates once for every single tooth on the cog it's engaged with. That's useful for getting a really high gear ratio. Yeah, maybe I could use a worm gear on my bike. Or a little less dead robot weight.
On pages 53 and 54 of your teacher-made packet, there are 2 boxes where you are identifying the simple machines in the real world around you. I would like for you to complete those 2 by writing, yes, I said writing, not drawing a line, writing the simple machine under the column that says Word. And this will be the end of today's lesson. I look forward to our lessons next week when we make some simple machines out of paper. You will need your scissors next week.